that describes this triangle and will allow me to solve for the two short sides? Here, let me label it. Let's label that A for apothem, and let's label, for the moment, we'll just call that X, which is just half of the base of that triangle. Okay? You can do this a couple of ways, but you really have to learn how to do it using trig. In other words, the case I presented left us with a 30-degree angle, but that's rare. Usually this will end up being, I don't know, 27 degrees, or because the only reason it's 30 is because we started out with a hexagon. Any polygon other than a hexagon, and this angle won't be 30 degrees. So we don't want to solve this problem based on our knowledge of a 30, 60, 90 right triangle. I mean, we could, but you're going to have to be able to solve multiples of these where it's not 30 degrees. So what trig function relates x to 1?
Sine. So it would be sine 30 equals x over 1.
Sine of 30 equals x. So x is 1/2. Right? Sine of 30 is 1/2. So that's 1/2 there. And what trig function is going to allow me to solve for A?
Tangent 1/2 over A.
Tangent of what? 30?
Tangent of 30, or you could do cosine of A over 1, or A cosine of A.
That actually might be easier, right?
Mm-hmm. Is that what you can do? Tap on trig.
Cosine of 30 degrees equals A over 1, or A, and that's √3 over 2. So now we have the apothem. And so plug it in. What's A going to be?
It's going to be √3 over 2.
Now let's start with the 1/2.
Oh, okay, 1/2 times √3 over 2.
Side length?
Times 1.
Number of sides?
6.
So what does that give us? 3 √3 over 2?
Yep.
That's the area. Now, let's change the problem slightly, and just so we do at least one of them, let's make this a 7-sided figure. Okay. I'm not going to try to draw it because I have problems trying to draw odd-sided regular shapes. So now what is this angle right there? You're going to need a calculator probably.
Okay, my calculator literally just ran out of batteries today.
Okay, get mine out.
Or I just got one. Okay.
What's that?
I just got a calculator. So what's the calculation I need to do?
To figure out what this angle is here, that I check marked on a 7-sided figure.
Okay, so times 5.
What calculation are you doing?
I'm doing 180 times 5 divided by 7.
Actually, we don't need to do that one. In other words, we don't really care what the outside angles are. We're trying to figure out the inside angle. There are 7 triangles in a septagon. So what is the measurement of each of those angles?
Oh, okay. 1 second.
So it's 360.
51.4.
360 divided by 7, and then cut that in half, because this is only half. That apothem always bisects that angle.
So 25.7.
And what is the equation for figuring out x and a?
Sine of 25.7 is x, and the cosine of 25.7 equals a.
Okay. And so the area would be 1/2 times the cosine of 25.7 times twice x, twice sine of 25.7 times 7. In other words, the side length is always 2 x's.
Mm-hmm.
And in this case, x isn't going to be 1/2. So the side length is not the same as that diagonal length. All right. Let me see if I can find a problem that mixes it up a little bit more than that. Okay, a regular dodecagon. Here. Let me write the details down here. We have a regular dodecagon. What? How many sides is that?
Dodeca, isn't that 12?
So it's 12-sided.
Mm-hmm.
And the information we have is that it has a side length equal to 4.3 and a radius of 8.3. So what's the area?
The radius is the apothem, right?
No, actually. The apothem goes from the center at a 90-degree angle to the middle of the side, whereas the radius goes to the vertex of the side. In other words, in our previous problem, which I erased, this was the radius, this was the apothem. Notice that the apothem comes straight down at a right angle, whereas the radius is always on the side of one of those triangles that's being fit in there. Okay?
Mm-hmm.
So, remember our formula. Area equals 1/2 apothem, and in this case, I'm going to call Sn the perimeter. Okay? Because we can get the perimeter pretty easily. What's my perimeter?
4.3 times 12. 51.6.
So So now all I have to do is figure out the apothem. Well, the apothem always comes down to a half of a right triangle like this. A is the apothem.
The angle is 15 degrees.
And the radius is 8.3. So it becomes the same problem as we had before. And actually, it's now a little easier because now the only thing you need is A. You don't even need that. We've already figured that into the perimeter. So the cosine of 15 degrees equals, this is a little different because it's not 1, but it's the cosine of 15.
Sorry.
Is that on your end? You okay?
Yeah.
In other words, A here is going to be 8.3 times the cosine of 15 degrees. And then once you get A, that's all you need. If you plug it in directly into that formula there, we've already got the perimeter. Looking for others. It's actually a lot better if you can send me your problems. Merely because, well, there's lots of reasons. I'm kind of shooting in the dark here as to what problems to give you, and I don't know that that's exactly what you're going to cover in class. Still looking, hold on. That's all I have here are hexagons. Okay. Some of these questions I don't understand. They're so simple. They give you a pentagon and they give you the area of one of the triangles and they ask you for the area of the whole thing. Oh, I mean, then you multiply by 5. Let's see if there's any. I think that pretty much covers it for regular polygons. What other kind of problems have you been working on besides regular polygons?
That's really all we've been working on.
It's the sum of the exterior angles of all polygons.
Sorry, what?
It's the sum of the exterior angles of any polygon. And here's what I mean by the exterior angles. If you take one of these lines and extend it, and you go in the same direction each time, in other words, I'm working my way counterclockwise.
Yeah.
So angle 1, angle 2, angle 3, angle 4, they always add up to the same number, no matter how many sides the polygon has?
360, right?
Yep. So even if it were 20 sides, each of these angles is going to be really small. That's actually not a bad way to figure out what that angle is, if you think about it.
Yeah.
In other words, you take 360, divide it by the number of sides, subtract that from 180, and you have that angle, which I suppose is not any easier than using the n minus 2 times 180 divided by n. Here's one that's not a regular pentagon. Let's have a look at this. This is the pentagon that I can draw. Most of them I can't. A regular one I can't. This I can draw because it looks like home base. What's that angle there? And that angle? And they're the same in this case. And these are all right angles. Excuse me. So how are we going to figure out what these angles 1 and 2 are?
We need to figure out what the overall interior angle measurement of pentagon is. So you do 180 times n minus 2. So it would be 180 times 3, which is 540.
Okay.
And then subtract 390-degree angles.
270.
And then divide it by 2.
Okay. Now notice we could not use the exterior angle theorem on this one. The exterior angles only add up to 360. Well, let's see. That would be 90 here. That would be 55. That would be 90. That would be 55. Or 45, excuse me. 45 down here. And that would be 90. So I got 270 plus 90. Interesting. The sum of the exterior angles on this also add to 360. And in fact, that theorem might be, regardless of whether it's a regular polygon. It is. Yeah, the sum of the measures of the exterior angles of a convex polygon add to 360. Did we go through? No, we didn't. This is a convex. I got my definitions backwards. I thought this was a concave polygon. And I thought a convex polygon would be something like that. Apparently it's the other way. This is convex, and this is concave. You know what the difference between them are?
No.
There is no way in the convex polygon that you cannot see all 5 corners from anywhere in the polygon. Whereas in the concave polygon, if you enter down here, you can't see somebody that's over there. In other words, to connect 2 points in a concave polygon, you have to go outside the polygon. Whereas convex polygons, you can always connect any 2 points. All right. Do you have any idea, Cole, where you're headed next after this? It looks like, yeah, this is the chapter after circles. How'd you do on the chapter in circles? You good there?
We didn't do it yet.
Oh, they didn't do it. Oh, I was going to say there's a lot in that chapter.
Yeah.
And it's stuff that you haven't been taught yet either. It's not SAT circle stuff. It goes quite a bit beyond just area and circumference. Interesting. Well, that's almost certainly where you're going next. I think. Let me just check past this chapter. Ooh, sectors. I don't know. I guess we'll deal with it when you get there. But can you next Monday, can you think about sending me review material?
Yeah, I'll try, yeah.
If you can. Whether it's taking pictures out of your book, if you have to do that, that's fine. It's easy to do. Take a picture with your camera and send it to me. Or taking pictures of review material that the teacher has given you. But it's so much easier to have a session if you're giving me problems.
Yeah.
Because for one thing, we can go straight to the problem that you may not know how to do. You might know how to do 11 out of the 12 problems on there, but we can hone right in, which is kind of hard to do today. But this was still worthwhile. So, all right, Cole, I will talk to you next Monday.
Talk to you next Monday.